Okay, we have been talking about electroosmotic micropump and we are discussing cascade electroosmotic micropump. In case of electroosmotic micropump through a microchannel, we saw that if we reduce the size of the microchannel, the pressure capability of the micropump increase, okay, but the flow rate is reduced with reduction in the channel size. So, we thought of going for cascade electroosmotic micropump because still to achieve high flow rate and high back pressure across a single channel micropump, we need to apply considerable amount of voltage. So then we considered a case where there is net 0 voltage drop across a stage and we are still able to get pumping action, okay. By going for cascade electroosmotic micropump, we are able to increase the pressure capability of the micropump, okay. So we are considering one such case here. So if you look at here, we are considering a cascade electroosmotic micropump and we just try to consider a single stage enclosed by this dotted line, okay. So for a single stage, what we are doing here is the part 1 of the channel, the first part of the channel is divided into many small channels such that the pressure capability is more, and the second part of the channel is a large having large size, so that we obtain larger flow rate, okay. So let us analyze one such stage here, okay. So we say that the part 1 of the channel, okay, part 1 has n square narrow channels, so we can say A1, which is the size of the part 1 of the channel, is A2 divided by n, okay. A2 is the size of the channel in part 2, and we had defined a parameter called size ratio alpha, which is the ratio between the size of the first part of the channel divided by size of the second part of the channel is equal to, so A1 over A2 will be 1 over n, okay. And we had used our hydraulic star, which is given by 8 eta L divided by pi A2 4 and Q electroosmotic star, which is given by pi A2 square epsilon xi divided by eta L into delta V, okay. So the two parts of the channel have same overall flow cross sectional area, so let us say A1 equal to A2, let us call it some A, okay. So n square, so we are saying that we have n square narrower channels here, okay. What you see here, we have n square narrower channels, so n square into pi A1 square is going to be pi into A2 square, okay. So with these definitions we can find out the hydraulic resistances, the hydraulic resistances and the electroosmotic flow rates for the two segments of the channel. We can say the Q electroosmotic 1 equal to 1 over n square into Q U star and Q electroosmotic n. So n is for refers to n square parallel channels. Okay. So, this subscript n refers to n square parallel channels. So, we have n square number of parallel channels present in the part 1 of the network. So, QN would be QU star. Okay. And the electroosmotic flow rate in part 2 will be equal to minus QEO star. The negative sign, as we discussed earlier, is because of the direction of the electric field. Okay. And similarly, we can define the hydraulic resistance. We can define our hydraulic 1 as n to the power 4 into R hydraulic star, and R hydraulic n for n square different channels is going to be n square into R hydraulic star, and the hydraulic resistance for the second part of the channel is going to be R hydraulic star. Okay. The second channel is the reference channel. Okay. Now, if you go for mass conservation, but we say that the total amount of the fluid flow that comes in from comes through the part 1 of the channel is equal to the same that goes through the second part of the channel. If we say that, then you can write Q equal to Q EON. So, this is the total flow that is coming through n square different n square small channels, okay, plus 0 minus Pc divided by R hydraulic n. Pc is the central pressure in the previous case that we had studied, is equal to QEO star minus 1 over n square into Pc divided by R hydraulic star. Okay. So, we just substitute for R hydraulic n and Pc from here. Okay. This is the R hydraulic n, and we can write. So, this is the flow rate in the part 1 of the channel. Similarly, for part 2 we can write Q equal to QEO2 and Pc minus delta P divided by R hydraulic 2. So, that will be equal to minus QEO star plus Pc minus delta P divided by R hydraulic star. Now, if we solve these two equations, we can get an expression for the central pressure Pc and Q. Okay. So, if you solve, we will get Pc equal to 2 n square divided by n square plus 1 into R hydraulic star Q electroosmotic star plus n square divided by n square plus 1 into delta P. Similarly, we can say Q, the flow rate, equal to n square minus 1 divided by n square plus 1 into Q electroosmotic star plus 1 over n square plus 1 into delta P divided by R hydraulic star. Okay. So, these two are the expressions for the central pressure and flow rate. Now, from here we can calculate what is going to be the flow rate when the back pressure is 0, that is the free flow rate, and what is going to be the back pressure when the flow rate is 0, okay, the maximum pressure capability of the pump. So, if you do that, If we do that, we can calculate the zero flow pressure capability and zero pressure electroosmotic flow rate. So, we can write PEO is going to be n square minus 1. So, this is when the flow rate is 0. Okay. So, this is when the Q equal to 0. So, if you do that, if put Q equal to 0, we can find what is going to be the pressure capability. Okay, n square minus 1 into R hydraulic star into Q EO star, which will be 1 minus 1 over n square into R hydraulic 1 into Q hydraulic 1. Okay. So, this is the zero flow pressure capability. Similarly, we can find the zero pressure drop flow capability. Okay. So, here delta P is going to be 0. So, we can find the free electroosmotic flow rate as n square minus 1 divided by n square plus 1 into Q electroosmotic star, which we can also write as 1 minus 1 over n square divided by 1 plus 1 over n square into Q electroosmotic n. Okay. Okay. Now, in these two equations, if we say that n is increasing continuously, if we have more number of smaller and smaller channels in the part 1 of the electroosmotic pump, then we would see that the pressure capability will be same as the pressure capability of a single small size electroosmotic pump, okay, because of the smaller channel, okay, as n is very high. And when n becomes very high, the flow capability of the single stage electroosmotic pump will be that of the second part of the channel, okay, where the channel cross section is A2. Okay. So, if you look at here these two equations, okay, we can see that as n increases, so n is number of sub channels in part 1 of the channel, number of sub channels in part 1 goes up, then you can see that this term is going to be 0. Okay. So, the pressure capability is going to be R hydraulic 1 into Q hydraulic 1, which is the pressure capability of a single sub channel. Okay. So, what we see here is that the pressure capability of 0 voltage electroosmotic pump stage approaches that of a single narrow sub channel, that of a single narrow sub channel. And so, this is, and we can also observe that as n is very high, the electroosmotic flow rate, there is a small correction here. So, this is going to be Q EO2. So, when n is very large, you can see that the Q electroosmotic is equal to the electroosmotic flow rate in case of the channel part 2, okay, section 2. So, the free flow rate would approaches that of the wide channel 2, okay. And it is possible to join several of these stages in series, so that we can increase the pressure capability of the micropump further. So, we have considered just one single stage, and we saw that as we increase the number of sub channels, the pressure capability is going to be that of a single sub channel, narrow sub channel, and the flow capability will be that of the wider channel, which is the channel 2, part 2 of the micropump. And it is possible to join many of these stages in series to further increase the pressure capability of the micropump, okay. So, with that we complete the electroosmotic micropump, and now let us proceed to talk about what is electrophoresis, okay. So, we talk about electrophoresis. So, here we talk about electrophoresis is the movement of charged particles in a stationary liquid, okay, and these charged particles may be dissolved or undissolved in a stationary liquid by applying electric field, okay. So, we can define electrophoresis as the movement of charged surfaces in a stationary liquid or relative to a stationary liquid due to applied electric field. Okay, so that is the definition of electrophoresis. Now, if you see here, we have a liquid medium. Okay, so this is the medium, and we have the cathode here and anode here. So, the electric field is in this direction, and in the medium we have some charged particles. We have positive charged particles and negative charged particles, and when you apply this electric field, the positive charged particles will try to migrate towards the cathode, and the negative charged particles will migrate towards the anode. Okay. Now, when you are talking about a medium which has non-zero electrical conductivity and we have electric field in this direction, we would always have electroosmosis coming into play, and if the zeta potential is negative, then the electroosmosis is going to occur in this direction, and so we would always have electroosmosis present because of non-zero conductivity of the medium. But because of the attraction of these charged particles to opposite electrodes, these charged particles will occupy a space between the two electrodes. Okay. So, these charged particles will be separated between these two electrodes depending on the sign of their charges. Okay. Now, here if you consider one such spherical charged particles, okay. So, we consider this particle of radius a and charge is jd, okay. So the particle radius is a and the charge is jd, and we consider that this particle is in a medium which has a low electrical conductivity, so that we do not have any induced charge coming around the particle. So the fluid has low electrical conductivity, so that no induced charge. Okay. So in that case we can write down different forces. So the electric force is given by the charge into electric field. So F electric is the charge into the electric field, and because of the electric field, when this spherical charged particle would tend to move, it will be subjected to drag force, okay, as you see here. So you would have drag force opposing the motion of the charged particle. So and that is given by minus 6 pi eta a into the velocity of the particle, let us call it the electrophoretic velocity. Okay. So if the velocity is in the positive x direction, then the drag force will be in the negative direction. So this is given by the negative sign, okay. Now to find an equilibrium of the forces that are acting on the particle, we can do a vector sum of these two forces, okay. So for equilibrium we can say that the total force is F electric plus the drag force, and so we can write that Jd into electric field is going to be equal to 6 pi eta a into electrophoretic velocity. So from there we can find that the expression for the electrophoretic velocity is equal to charge divided by 6 pi eta a into electric field. So you can see that the electrophoretic velocity is aligned with the electric field if it is a positive charge particle, and it will be aligned with it will be in the opposite direction if it is a negative charge particle, okay. So this ratio charge to 6 pi eta a, we can call it the ionic mobility, okay, mu ion into electric field, okay. So this is called the ionic mobility. What you see here is that the electrophoretic velocity also depends on the charge as well as the size of the particle, okay, and this dependence is exploited to use electrophoresis for shutting off different bioparticles like DNAs, okay, and proteins also, okay. So as the electrophoretic velocity depends on the charge and the size of the particle A. So this is used to, so electrophoresis is used to separate bioparticles such as DNA and also proteins, okay. So you can define a parameter. So we have defined the ionic mobility here. So the electrophoretic velocity u p or u e p is given by mu p into electric field, okay. So this is the ionic mobility, and the electroosmotic velocity u EO is given by epsilon xi electric field divided by eta, okay. So mu 0 is given to epsilon into xi over eta, okay. So this is the electroosmotic mobility, and this ionic mobility also known as the electrophoretic mobility, electrophoretic mobility, okay. Now in a typical situation when we have charged particles in a liquid and we apply an electric field across the ends, depending on the jitter potential we would have the electric field direction, we would have the electroosmosis taking place, and normally this electroosmosis is very strong as compared to the electrophoretic velocity, okay. So these charged particles irrespective of their charges will be always carried by the electroosmotic velocity, electroosmotic flow, but since depending on the charge they will be attracted towards the opposite electrodes, they will be located at different locations between the ends of the channels, okay. So that is how electrophoretic separation would occur. So the net velocity of the particle, net velocity will be the vector sum of the electrophoretic velocity and electroosmotic velocity. So u would be the electrophoretic velocity plus minus E0. So depending on the direction of the electrophoretic velocity with respect to the electroosmotic velocity. So this will be mu p plus mu 0 into electric field, okay. Now let us consider this example. So this is the example where we have a this is a buffer, this is a buffer, and we have charged particles present here, and here the electroosmotic flow is occurring in this direction, and the charged particles are attracted towards the opposite terminals depending on their charges, and they are also transported depending on their mass. Okay. So, the mass to charge ratio is what defines the movement of these charged particles with respect to the electroosmotic flow. So, for a particle which has very strong charge, okay, so strong positive charge and less mass, it is attracted more towards a negative electrode. Okay. And if you compare A2 plus with A1 plus, since the charge is more here, it is attracted more towards the negative electrode as compared to A1 plus. Now, if you compare A1 plus with the larger A1 plus, here the charges are the same, but the mass of this charge is higher as compared to this charge. So, this charge particle is leading towards the negative electrode as compared to this charge particle. So, depending on the mass to charge ratio, we would have a distribution of these charges between the two terminals, and so that would separate this charge particle, which is known as electrophoresis. Okay. So, the electrophoresis enables separation of charged particles based on charge to mass ratio, charge to mass ratio between the electrodes. Okay. Now, we talk about the ionic mobility, So, mu ion is ZE charge divided by 6 pi eta into the size of the charge particle. So, we try to do an order of magnitude estimation for the ionic mobility. Let us say the charge is 1 coulomb, okay, and the viscosity is 1 millipascal per second, millipascal second, and if the radius of the particle is charged particle is 0.2 nanometer, the ionic mobility is about 4 into 10 to the power minus 8 meter square per volt second. Okay. Okay. So, with that we complete our discussion on electrophoresis. Now, let us move on and discuss dielectrophoresis. Okay. So, dielectrophoresis is a technique that can be used to separate neutral objects like cells, okay, by applying a non-uniform electric field. We have seen electroosmosis, which is used to drive the bulk of the fluid by applying an electric field, okay, and when the fluid is having non-zero electrical conductivity, it is an ionic liquid. Then we saw electrophoresis, which is the separation of charged particles in a liquid, okay, and that charge, the separation of these charged particles occur because of an applied electric field. Okay. Now, we talk about dielectrophoresis, which is the separation of neutral particles like cells when we subject the particle to a non-uniform electric field, and there is a difference in between the dielectric constant of the particle and the dielectric constant of the medium in which it is present. Okay. So, let us talk about dielectrophoresis. Okay. So, we define dielectrophoresis as the movement of neutral charged neutral particles in a dielectric fluid due to an inhomogeneous electric field. Okay. So, we can create this inhomogeneous electric field by various methods. One approach is if we can use asymmetric electrodes, okay, where the electrode configurations are different, we should be able to create an non-uniform electric field. Okay. And let us say we have one such neutral objects in an electric field. When you have neutral object which is having a dielectric neutral sphere, for example, in an electric field, will polarize that neutral object. Okay. So, here we can write, if we have a sphere or any object in an electric field, then we would induce polarization in that object. So, the polarization is given by epsilon 0 into psi into electric field. This we had looked at when we talked about electrohydrodynamics. So, the object or the sphere will get polarized, where psi is the susceptibility. Okay. Now, when this object or sphere gets polarized, we would have the induced dipole moment. So that will be equal to alpha into the electric field, and alpha is the polarizability. Okay. So, this is the polarization, capital P is the polarization, and the small p is the induced dipole moment, okay, where alpha is the polarizability and E is the electric field. Now, the dipole force that will act on this dipole moment, the dipole force acting on the dipole moment in non-homogeneous electric field is the dielectrophoretic force, okay, is equal to the dipole moment dot del into electric field. Okay. So, what we are considering here, we have an object in an electric field, okay, and when you put that object in an electric field, it gets polarized. So we know what is its polarization, okay, and that is going to be epsilon into susceptibility into the electric field. Because of the polarization we would have the two, let us say in case of dipole we would have charge concentration, opposite charge concentration at two different regions. So it will induce a dipole. So because of the presence of the dipole we would have a dipole moment, okay. So the dipole moment is given by the polarizability into the electric field, okay, and because of the dipole moment the object will be subjected to a force which is also called the dipole force or dielectrophoretic force, and that will be dipole moment dot gradient of the electric field. So there has to be a non-uniform electric field for this dielectrophoretic force to occur, okay. So that is what we see here. So it is dipole moment dot gradient of the electric field. Now let us talk about the induced polarization, induced polarization and DEP. First we talk about, let us say we have a sphere in a medium and this dielectric constant is epsilon 2, the medium dielectric constant is epsilon 1 and this electric field is non-homogeneous, okay. So this will be subjected to electric displacement, okay. This is also something that we had discussed earlier. When we have an electric charge in a medium it will lead to electric displacement, okay. In this case we are talking about presence of an object of dielectric constant epsilon 2 in a medium having dielectric constant epsilon 1. So it will be subjected to an electric displacement, okay. So the electric displacement D is given by epsilon 0 into electric field plus the polarization, okay. This is also something we had looked at earlier. So this will be epsilon 0 into 1 plus psi into electric field, so that will be equal to epsilon into E, okay. So with that knowledge we will go ahead and talk about the the dielectric force that acts on a point dipole, okay. So we talk about dielectric force on a point dipole. Okay. So before we talk about the dielectric force, let us talk about the effect of, first we talk about the effect of point dipole in a dielectric fluid. Okay. So this is something we talk about first. So this is the image where we see a point dipole, okay, plus q and minus q, okay, positive charge and negative charge separated by a distance d. So it constitute a point dipole, okay. Now what is the effect of this point dipole on the surrounding, okay, that is something we are interested to find. So what we can see here is that the point dipole moment due to the point dipole is going to be q into d, okay. And because we have a positive charge, so plus q at plus d by 2 and minus q at minus d by 2, okay. So that is we are talking about this point dipole in a space, and so we are talking about around here plus d by 2 minus d by 2, okay. So this is the dipole moment, okay, and these are the charges. Now because of these dipole moment or the charges, okay, one positive one negative charges, we can find the potential distribution, okay. So we can find the phi because of the dipole. Let us say at any point r, okay, any random point r somewhere here, okay, is going to be plus q divided by 4 pi epsilon into 1 divided by r minus d by 2, okay, plus minus q divided by 4 pi epsilon into 1 by r plus d by 2, okay. So this is the definition of the potential distribution due to a point charge, okay, and these are the position vectors of any particular point that we are talking about, okay, any particular point we are talking about. So what it means is that if you have a point dipole plus q minus q separated by d, the potential at any point with position vector r with respect to the origin is going to be like this, okay. So you can approximate this as 1 over 4 pi epsilon into the dipole strength P into r divided by r cube, okay. So this is the r is the distance from origin. So this will be P over 4 pi epsilon into cos theta over r square, okay. So if you look at the geometry, r over the magnitude of the r will be cos theta, so you will get P over 4 pi epsilon into cos theta over r square, where theta is the angle between the dipole P and point r. So you can find phi, the total potential at any point is going to be the potential because of this dipole, and if there is any external field that is available, okay. So the total is at r is going to be, so we can call this as b cos theta over r square plus phi rest. So apart from the dipole, what is the potential effect, and so you know we are introduced this b here. So the dipole strength P is going to be 4 pi epsilon into b, okay. So b is P over 4 pi epsilon as we see here, okay. So with that let us stop here.